Those slick headlines about ESA's Euclid telescope and the DESI survey keep showing up with the same promise. A new map of the universe, a new clue about dark energy, a better measurement of how space is changing. As of 2026-0107, the pictures look almost innocent. Pinpricks and spirals and fuzzy ovals, a calm census of galaxies. But the story underneath those maps is not calm at all. It's a story about discovering that the universe behaves like a car that speeds up even though nobody can find the gas pedal. Take something familiar, toss a ball straight up. The moment it leaves your hand, it starts losing speed. Not because the air is mean, but because gravity is always pulling downward. Or picture a skateboard rolling on a flat road. Without pushing again, it doesn't mysteriously accelerate. Motion coasts and forces act like pushes and pulls. Now scale that intuition up. Galaxies are not just pretty lights. They're heavy. Heavy things attract other heavy things. Put two galaxies in empty space, and gravity pulls them together like two balls on a trampoline, rolling toward the dip. So if everything in the universe is moving apart, if the distances between galaxies are growing, gravity should act like a brake. Not an instant stop. Just a slow, steady tug that makes the expansion ease off over time. That expectation is so basic, it almost feels like common sense. And then astronomy delivered the punchline. The expansion is not easing off. The expansion is picking up speed. That claim sounds like philosophy until it turns into a measurement. The trick is that the universe does not hand out rulers. Distance in space has to be inferred using light. Here's the everyday part of the trick. A porch light looks dimmer when it's farther away because the same light gets spread over a larger and larger invisible sphere as it travels. Double the distance, and the sphere's surface becomes wider in two directions at once, so the light is spread over about 4 times the area. 10 times farther means about 100 times the area, because 10 times 10 is 100, so the light looks 100 times dimmer. Astronomers use that idea by hunting for objects with a known true brightness. If the true brightness is known and the apparent brightness is measured, distance drops out of the comparison. The drama begins in the early 1900s when Albert Einstein built general relativity, his new theory of gravity, where gravity is not a mysterious force reaching across space, but the result of space and time being warped by mass and energy. Einstein tried to apply it to the whole universe, and like most people at the time, assumed the universe should be static, not expanding, not contracting. The equations fought back. Gravity made a static universe unstable. To hold the cosmos still, Einstein added a mathematical fudge factor, later called the cosmological constant, a kind of built-in outward push. Then, Edwin Hubble looked up in the 1920s and found the universe wasn't holding still anyway. By measuring distances to galaxies and comparing them to how their light was shifted toward redder colors, a stretching of light that happens when the source is moving away, Hubble showed that distant galaxies are generally receding faster. Space itself is expanding, carrying galaxies along like dots on a balloon's surface, as the balloon inflates. Once expansion was real, the argument about breaking became urgent. If the universe started expanding, gravity from all the matter in it should slow that expansion down. The question became, by how much? In the 1990s, 2 teams went after an audacious measurement. Instead of tracking galaxies directly, they used exploding stars called type Ia supernovae. A supernova is a star's catastrophic end. A type Ia specifically happens when a dense stellar remnant, a white dwarf, roughly Earth-sized but packed with about the mass of the sun, gets pushed over the edge. When it reaches a critical condition, the explosion is remarkably consistent in true brightness. That consistency is not magic. It comes from physics. The white dwarf's material is held up by a pressure that comes from quantum rules rather than heat. Add too much mass, and the support fails in a predictable way. The result is a fairly standard kind of blast. Not perfectly identical. Astronomers learn to correct for small differences, but consistent enough to act as a standard candle, meaning a light source with a known wattage. So the plan was simple to say and brutal to execute. Find type Ia supernovae very far away, measure how bright they look, and also measure how much their light is stretched toward red. The stretch, called redshift, acts like a timestamp. Higher redshift generally means seeing the supernova further back in time when the universe was younger. If the expansion had been slowing, those ancient supernovae would sit at one place on a graph of distance versus redshift. If the expansion had been speeding up, they would land somewhere else. In 1998, the supernovae landed in the somewhere else. They were too dim. Too dim means too far. And too far for a given redshift means the universe expanded less in the earlier part of its history and more later on. In plain language, the expansion rate has been increasing. Nature almost never allows a single dramatic result to stand unchallenged. Astronomers attacked their own conclusion from every angle. Maybe dust between galaxies was dimming the light, but dust usually reddens light in a telltale way, and the effect didn't match. Maybe distant supernovae were fundamentally different, but nearby supernovae could be studied in detail, and the standard candle corrections kept working. Maybe the surveys were biased toward finding only certain kinds of events. So the teams built better searches, found more supernova, cross-checked methods, and the acceleration stubbornly remained. Then, independent evidence arrived from completely different cosmic fossils. One is the cosmic microwave background, a faint afterglow of the early hot universe, a baby picture taken when the universe first became transparent. Another is the pattern in how galaxies cluster on enormous scales, where an ancient pressure wave from the early universe left a preferred separation distance, like a ripple frozen into the distribution of galaxies. That ripple pattern is what projects like DESI and space missions like Euclid are designed to measure with obsessive precision. It's a standard ruler instead of a standard candle. Different tool, same ambition, reconstruct how fast the universe was expanding at different times. And that brings the story back to those modern maps. Euclid is not just collecting pretty galaxies. It's collecting statistics. How clumped galaxies are, how those clumps change with time, and how the geometry of the universe stretches distances. DESI is doing something similar from the ground by taking spectra, splitting light into colors, to get precise redshifts for enormous numbers of galaxies. The open problem is not whether acceleration exists. The open problem is what causes it. The simplest explanation is that Einstein's old fudge factor was not a mistake, but a real property of space. Empty space has a tiny, steady energy that produces a repulsive gravitational effect on the largest scales. The name dark energy is really a placeholder label for that idea. But there's a deeper headache. When quantum physics is used to estimate how much energy empty space should have, the naive answer is wildly larger than what cosmic acceleration allows, off by an absurd number of digits. That mismatch is one of the most famous unsolved problems in physics. Another possibility is that gravity itself changes on enormous scales, so general relativity needs a correction when the universe is the laboratory. So what could actually decide between these options? Measurements that don't just track expansion, but also track how fast cosmic structure grows. A universe with a constant built-in push expands one way and makes galaxies clump together another way. A universe with modified gravity can mimic the expansion while changing the clumping. Euclid's maps of galaxy shapes and DESI's redshift surveys aim directly at that difference. Future observatories, like the Vera C. Rubin Observatory and the Nancy Grace Roman Space Telescope, add even more leverage. Even gravitational wave events can help. When two neutron stars collide, the wave signal reveals their distance without needing a standard candle at all. A standard siren that checks the whole distance ladder from a different direction. So the next time another Euclid or DESI headline floats by, it's worth hearing the subtext. Those maps are trying to answer a brutally simple question that everyday intuition says should have an obvious answer. If gravity pulls things together, why is the universe's stretching speeding up? That question has a strange kind of beauty. It connects a tossed ball slowing down to the brightness of a distant explosion, to the fate of all galaxies. The same logic, light spreads out, signals travel, gravity shapes motion, works from a streetlight to the edge of the observable cosmos. And the lingering mystery is almost personal. Is cosmic acceleration a property of empty space itself, or a clue that the law of gravity is not finished yet? Like if this was interesting, Hit the subscribe for more and turn that notification bell on.